For the talk today, I'm going to start off with just rollups in general. Then we have to go through a brief segue into bridges, and then I can talk about optimistic fault proofs. This is where optimistic rollups get their name and what makes an optimistic rollup, this optimistic part. Lastly, we've done all of this work, and I'll talk about how rollups actually scale Ethereum. The rollups. Why do we want them in the first place? Because they're basically a way to scale Ethereum. This means more block space and cheaper transactions. A point of reference is that Ethereum is doing about 15 transactions every second. If you add up all the transactions per second on rollups which settle down to Ethereum, that's about 200 to 300 transactions per second. A single rollup like Base, which uses the OP stack, is processing about 150 transactions per second, 10x what Ethereum is. And you can have many more rollups the size of Base that land on Ethereum. So right now, Ethereum's too expensive. Rollups are a way to have cheap blockchains. Okay, what is a rollup? It's a blockchain that uses another blockchain for data availability and ordering. I'm going to be coming back to this definition a lot. This is the core of what it is. Now our first part is going to go through what a blockchain is. Then I'll dive into data availability in the context of rollups, go through how ordering applies to rollups, and lastly we'll give a high-level overview of what rollups look like. Okay, there's a couple key components of a blockchain. We have some state. This is user balances. Bob has 10 ETH, Alice has 1 ETH, etc. And then Ethereum is also special. It has smart contracts. These can be further balances like ERC20 tokens, USDC, USD Tether. You can also store any information you want in the smart contract state. If you want a log of did it rain today, you can store that on the blockchain. Then we have transactions, which are users sending funds to each other and also updating the state. So you can set a transaction to report, did it rain today or not? And then lastly, we have a state transition function, which is how we apply the transactions. And a key part of this is that it's deterministic. Everyone with the same transactions and the same starting state will end up at this same final state. This actually happens quite a lot because every single node in the blockchain network is executing these transactions on their own and getting to that same state. Okay, and then just some quick examples again. Statements around like Bob has 10 ETH, that's a state. Bob sending 1 ETH to Alice, that's a transaction. Updating this balance, state transition function. And then lastly, the state transition function has to reject transactions like Bob trying to send 100 ETH. If he only has 10 ETH, he doesn't have that money to send. So the state transition function defines how you process transactions, but it also defines what you cannot process, what's valid and what's invalid. Okay, and then we also have consensus as part of a blockchain. And there's two subcomponents to this. We have a total ordering, which says Alice's transaction happens before Bob's transaction, just one after another. And then we have this slightly more complex concept of a canonical head, and this shows up in a couple places later as well. And this says there's only one specific block at a height. Or kind of everyone agrees that this is the chain, this is the specific block. You can't have multiple people thinking that one block is kind of the potential head block. And the motivating factor behind this are double spend attacks. So Mallory can create 2 transactions. Each is individually valid. The first transaction is sending all of her money to Alice, and then the second is sending all of her money to Bob. And you can have 2 blocks with each of those transactions, but you have to agree which is the canonical block, which is the block that happened. Because if you have both of these blocks, and like some people think Bob has the money, but other people think Alice has the money, you kind of break the system. Mallory could convince both Alice and Bob to send her the money if she convinced those 2 actors that those blocks happen. But if there's only ever one single block, which is canonical, say it's Bob's block, Alice will never send the money to Mallory, and Bob can do the second leg of your transaction. So it's only one block. Okay, that's a quick review on blockchains. Now I'm going to talk about data availability. High level, data availability is that rollups put all of their inputs onto Ethereum. All of the transactions, basically all the transactions. And we do this for several reasons. The first is syncing. So as a rollup node operator, you can go over to Ethereum and find everything required to reconstruct the chain. The second portion is ordering. As we said, Ethereum has a total order of transactions. Because rollups submit their data and transactions to Ethereum, that then means when you're reading from Ethereum to reconstruct the rollup, you have a total ordering. So every rollup node operator sees the same view of what the transactions are. Yes?
Clarification on ordering. So you're saying the rollup inherits the ordering from Ethereum.
Yes.
But Ethereum gives it a block level ordering, but within a block it's up to the rollup to decide how to order, right?
Yes. Rollups mostly order the transactions on the rollup block, yes, but there is a little bit of yeah, we'll say, okay, when you have multiple competing rollup blocks, you then rely on Ethereum's ordering to figure out who wins. Does that make sense?
You're imagining a world with multiple proposers for the rollup, not like a centralized sequencer or whatever.
Even with a centralized sequencer, you still pick the first rollup block which has been submitted to Ethereum.
A quick question.
Yes?
The rollup blocks are on top of Ethereum at the second level.
Yes.
Is that right?
Yes. You'll often hear the term layer 2. In this context, rollup, layer 2, exact same thing. Layer 1 is Ethereum.
Okay, thank you.
I have a simpler question, I think, which is that, so you said that there's enough information on the layer 1 to reconstitute the chain of
Yes.
the layer 2. What literally, though, is actually posted of that on the layer 1? Like, what's actually posted?
Transactions. So
It's like call data and state, or like
it's not, it's the transactions. So we say like you have a contract which is storing when it's rained. And so if you have every transaction which has recorded what day it's rained, and you just apply all of those transactions, you will have the state at the end. So if you apply every transaction on the chain from a known start state, which is your genesis state, you will end up at the same state. And so it's only the transactions of the rollup which are put on Ethereum.
but it's posted as data, right? It's not like, it doesn't need to be executed.
That's correct. We just put like the inputs to the transactions. Yeah.
What's the role of layer 1 validators in like picking, say, competing rollups, right? They don't actually validate anything there, they just pick one?
They don't validate, you're correct. They don't even really pick one. In the way layer 1 in Ethereum sees rollups is just more transactions on Ethereum. There's not any special relationship.
Validator still has to chooses to include one or the other, yeah.
If two rollup transactions are competing for block space, it'll pick one on a tip. But like who bids higher? But generally, there's enough space on Ethereum for both. Awesome. Oh, one more question?
Yeah, what's the relationship between rollups and sharding?
Rollups and sharding. Kind of. If you look at the Ethereum roadmap, it was initially thinking about sharding and having like these different execution environments. Rollups have kind of replaced that, where you have multiple instances of a rollup and that horizontally scales. So you add another rollup, you get another execution environment. It's a little different to sharding in that the rollups don't talk to each other that much. So it's a slightly worse version of sharding, but it's also a more practical version of sharding. one more here.
So this data availability affects the scalability of rollup because you still need to put all the non-witness data onto the blockchain, right? So the fundamental issue with scaling is still there, right?
For technical reasons, storing the input data is much cheaper than executing the transactions and storing the post state. So Ethereum can store many, many rollups without ever actually executing the transactions.
The rollup, there will be apparently many. What the data or information they provide to base layer, Ethereum?
We'll talk the second half about how you can like do withdrawals, but right now we're just talking about they put the input data. Other question, or are you good? Okay, I'll go into proof system. Sorry, go ahead.
So you said that Base does 150 TPS.
Yes.
Can you give us a sense of what the capacity actually is? How big can we go on TPS?
That's a really good question. We measure we usually measure, like, at a technical level, we use a different unit, but ballparking numbers, we might have another 10x with a fair amount of engineering work with the current system, so maybe up to 1,500 on a single roll-up, and then there's a lot of work into how we do this, how we have many roll-ups. So if we have like 10 roll-ups, each at 150 TPS, how does that look like?
Yeah, following up on the first paper, how are rollups governed? What kind of governance do you see in the rollups? Are they basically centralized under the Ethereum Foundation, or can anybody who wants to have their own idiosyncratic rollup?
Anyone could do this. Basically, you can spin up your own rollup if you wanted to today, and then there's lots of different governance systems for many different rollups. Find me later, and I can talk about the various systems. Okay, last one I promise, and then we have to talk about proof systems a bit.
So from a practical perspective, how easy is it for a rollup to say that, okay, I want to change my data availability layer, I want to build on top of Solana and like not on top of Ethereum, and I'm just going to like start posting on Solana instead, so.
Pretty hard. Depends on the specific rollup tech. Talk to me later, I've done work on this. Cool, proof systems. We said by putting all the data on Ethereum, all the inputs, you can reconstruct the chain. And the proof system, which allows users to withdraw from the chain, actually is a type of node. It needs to be able to have that data to execute the chain. So that's kind of this last bit, and actually to the point of, if you put the data on another chain, doing withdrawals becomes tricky, because now you have to move data from that chain onto Ethereum and then do the withdrawal with that data. Okay. More on to ordering. Again, kind of high level, rollups, inputs to outputs, and we allow users to insert inputs, and this happens on Ethereum. So users can insert their own L1 transaction, which creates a layer 2 transaction. These are called deposits. Essentially, every single rollup has a form of this, and these transactions show up on the rollup in the same order that they show up on the layer 1. But we have many more transactions on the rollup than the layer 1 can support. So in addition, we have a second mechanism for sending transactions. This is where users send transactions directly to the sequencer. This is where some of the rollup transaction ordering is controlled by the sequencer. So you send it to the sequencer decides how to order it, and then it batches up all of these transactions, these layer 2 transactions or rollup transactions, into a single Ethereum transaction, and then shoves it on the blockchain. And so now, when the rollup's looking at Ethereum, it also sees these batch of transactions in addition to the user deposits, and uses that to create the rollup. And then, again, this is a state transition function. You'll also often see the word derivation because it's deriving the layer 2 chain from Ethereum. Okay. Now we have this kind of system level view putting it together. Yes?
Just a question on the ordering. So
Yes.
in the event that the sequencer is like censoring,
Mm-hmm.
then I kind of have to go through the first mechanism
Yes.
introduced.
Yes.
But given that the sequencer is still providing sort of an ordering of a certain set of transactions, and I guess it's not been injected in any way, how does ordering work in that world?
So it depends on the specific rollup. For the OP stack, these deposit transactions are inserted at the top of the layer 2 block, and then the batched transactions from the sequencer are after.
Okay, I see.
So maybe, can I just interrupt you and
Yeah.
maybe take a little bit of a step back, maybe for the benefit of all of those in the room that actually have not thought about rollups as deeply as many of the people who ask questions. So maybe can we do this like by an example also to understand the contrast. So for instance, somebody has an asset, wants to trade it with a Uniswap, within Uniswap, right? And so can trade it with a rollup on Unichain, or they can trade it on the mainnet. So can you describe the process of how each of these trades would manifest itself? What's the process to do one or the other, and how would it look like on the blockchain?
Right. So again, a rollup is a blockchain. So if you wanted to do a trade on Ethereum, you send your transaction to Ethereum. If you want to do a trade on Unichain, you send it to the Unichain sequencer. It's the same EVM and everything around that. Where the technical difference comes down to, there's a couple. The first is you have to move money from Ethereum to Unichain. You have to use a bridge, you have to use the deposit transaction. And then because of all this work we've done, your fees would be much lower on Unichain. But from user perspective, it's very, very similar, and we've done a lot of work to say it's blockchain. It has all the similar user-facing properties.
So what you're so just for clarity for everybody else, so I take an asset, I send it to a smart contract, which is the rollup contract of Unichain.
Yes.
Right? And then I can use it on Unichain.
Yes.
Right? Now again, for the benefit of the audience, how is that different from, say, using Coinbase, which is a centralized service, rather than using it on Unichain?
Right. So if you're using Coinbase to trade, you give your funds to Coinbase. Coinbase holds all their funds, and you can do your trades. With Unichain, the smart contract system means that Uniswap Labs and Uniswap Foundation, as the chain operators, cannot take your money. Coinbase has all of your money. And then on Unichain, this blockchain, you can do all of your transactions, versus Coinbase, you kind of swap inside their UI. Yes?
Yeah, just comment on the, putting your transaction on the L2 or directly, going. There is a big difference. Okay, so it's going to be much cheaper to go on the L2, but the finality, okay, there is a very big difference on the finality, especially with the, I think, to correct me if I'm wrong, okay, but with the optimistic, because you do not really know that your transaction will be included until it's actually there. We're talking about like weeks, not weeks, but days versus like minutes.
Right. There's two notions of finality. The first one actually is about order 30 minutes, and then the second one is this order week. And so only withdrawals have to go through this week-long delay. If you're an exchange, you can run a Unichain node and know within 30 minutes, is this always going to be true or not?
Okay. But with Ethereum, it's going to be 10 minutes, right? If you're going directly on Ethereum, okay, it's 10 minutes, because it's the time basically when the next block will come in.
It's like 18 minutes roughly on Ethereum finality on average. Their finality system's a little more complex, but it does take longer on a roll-up even than Ethereum. Yes.
what does the rollup replica has as data?
So this is, you're just running a Unichain node, and kind of as an exchange or as an end user, you want to know what's happening on Unichain, so you run a node. It's just like running an Ethereum node.
In terms of gas fees, is it cheaper if I want to do like moving money to Unichain, do a swap in Unichain and moving it back to Ethereum? It would be cheaper than doing the swap directly on Ethereum?
That specific sequence, probably not, because the withdrawal step incurs a long delay. It's a week. You either have to wait a week, or you have to find someone who's willing to provide you capital for that week in a fast liquidity withdrawal.
So reducing the cost is only if you're going to do multiple.
Yeah, so what we find is a lot of users kind of move their assets to a rollup and then continue to do most of their trading on the rollup. Cool. And back to our definition. Blockchain that uses another blockchain for data availability and ordering. Okay, so we got to talk about bridges very briefly. So right now, what we have a rollup, we have a blockchain. You can move money in, but we've talked a little bit about the withdrawals, and you kind of can't really do that at this point with what we've described. As outside observers, we can run an Ethereum node, we can run a Unichain node, and we can know exactly what's happened. We talked about this finality. Ethereum has a consensus protocol that claims to finalize after around 18 to 24 minutes. Unichain takes about 30 minutes to do finality. But Ethereum, inside the context of the EVM, inside a smart contract in Ethereum, you don't know what's happened on Unichain. And we need a bridge to connect the two. And kind of the core of the bridge is, what was the canonical block on Unichain? That's the essence of a bridge. And there's a lot of ways to get there. The first is a multi-sig bridge. Just trust me that I have said this is what happens. And it works great if you trust that multi-sig, and it works horribly if that multi-sig lies and does something that steals all the funds. The second are trusted execution environments. It's very engineering. You have some hardware which isn't going to lie, maybe. Then we have optimistic interactive proof systems. That's an optimistic fault proof. That's what I'm going to be talking about in the next section, and that's how optimistic rollups show that this is the canonical block from Unichain onto Ethereum. Lastly, we have zero knowledge proofs. Benedict after me is going to be talking about them and how they work. Cool. There's a lot of really good questions, which means this section might be a little skipped or go quickly, and find me later if you have more questions, because the fault-proof system is relatively complex. So I'm going to give an introduction, talk about execution steps and traces, which are the building blocks, talk about bisection, which is how we make this efficient. We have bonds, which I'll probably spend a little more time on, because the economic theory there is interesting, and we'll do a recap. Introduction. So the way optimistic fault proofs work is anyone can propose that a block is canonical on the rollup. So rollup block is canonical on Ethereum. Ethereum is where this all happens. And we say that if it's not been challenged, this proposal is assumed to be correct. This is optimistic. We optimistically assume people are being honest. But if it's not correct, how do we challenge this? How do we show that this was wrong? So the simplest fault-proof program or way of showing that this output state is incorrect is, let's just execute the entire rollup inside the EVM. We have all of the data. The Ethereum virtual machine, which is the smart contract layer inside of Ethereum, can do computation. But this isn't practical as a system because the EVM is very resource constrained. Again, many more transactions on the rollup than on Ethereum. And in addition, there's a lot of computation that happens outside the context of a transaction. But then, what if we only had to execute a small portion of the rollup inside the EVM? And this turns out to work, and this is how we do optimistic rollups in practice. Okay, So what is the smallest component of execution? It's this execution step, and then we'll build it up into execution traces. An execution step is a single CPU instruction, adding two numbers, comparing two numbers, jumping based on a result of the comparison. This is what every little bit of code gets compiled down to these very small steps. Here's an example of a CPU state. We have some registers, just some values, and we're ORing them together in this example. But this is representative of the smallest step, and we have many, many of these. And executing this on chain is actually really easy. So then we have these many, many steps, and now we're going to build them up into an execution trace. We're going to start at some agreed on state. We call this the absolute pre-state, and we just iteratively apply this execution step. And something else, this execution step is deterministic. And so we kind of get this sequence of steps. This diagram has 8. In practice, it's about 8 trillion. 2 to the 43rd. A lot of rollups are in that ballpark of like 2 to the 42nd to 2 to the 44 steps. And it's a very, very large number, 8 trillion. But remember, every CPU in your phone, your laptop, is doing billions of steps per second. So with computers, we can actually feasibly compute these. Okay, and then we just have the mathematical definition. Our old friend, the state transition function, is just applying this pre-state going to a post-state, then we have this sequence. Okay, we have this way of doing this deterministic computation, and we said we can't do all of it on Ethereum, but we can do a portion of that. And bisection, or binary search, is how we do this. So I'm going to walk through this simple game. We have an honest trace, Alice, and an incorrect trace, Mallory. They're starting from A, and then in this example of the alphabet game, just iterating the alphabet is the correct move here. And then you can see between H and I, or H and W, index 8 is where they start to disagree. I'll just go through the moves. So we're going to have Mallory start. It's going to make a claim Z. And now we have this implicit range of A to Z, pretty large. But then Alice can move in and disagree and respond with the midpoint. And now we have 2 ranges, each half the size. And Mallory's going to respond again having the ranges. So the ranges get much smaller every time. I'm going to keep doing this. Alice is going to respond with G, again narrowing it. And we're going to respond one more time. And so now, what we've noticed is rather than stepping over every single point, we've taken a much smaller number of steps, and we've gotten to this point where we have G to H and H to I, or H to W as our range. This is a single step. This is the single CPU instruction that we can execute on-chain in our verifier smart contract. And then Alice is able to do this, and then Alice wins. And so this scales very well. When we're making these moves, there's one more component. Because this is very computationally expensive, it costs Ethereum gas, it costs off-chain resources, we want to disincentivize people from attacking. And so we have bonds to do this. For the OP stack, it starts at 0.08 ETH, it goes up to 300 ETH per side. Other rollups use different bonding system. It's a very interesting area on how to do these bonding systems well. And then whoever wins takes the other side's bonds. And then there is this one very interesting attack on the economic side is, can you outspend a defender? And our last example, Alice may know what the correct move is to defeat Mallory, but if they don't have enough money to put up the bond, they can't actually make that move on chain. And Mallory would win by default. And that's where this proof of whale attack is, where if the attacker can outspend the defender, they take all the defender ETH and the bridge ETH. Conversely, if the defender is able to actually defend, the attacker loses everything. So it's a very high risk, high reward. Cool. So we've gone through this optimistic fault proof system. Couple properties as a recap. They're practical. We can actually do this and have this on chain. because of this logarithmic scaling. We have one honest actor model where we don't need a complex, it's a complex system, but we don't need many actors. We only need one person to be correct. And lastly, as people have pointed out, there is a finality to it. It takes a week to do this, because otherwise a defender won't be able to respond in time.
Can I just quickly ask, where
Yes.
does the week come from?
It's a great question. It's kind of, everyone's kind of said, okay, this is the week. There's a couple factors. One of them is with like bridge hacks. Maybe you could fork Ethereum in a week. You also need to give people time to respond. So it's 73 transactions per side to play to the end. So that takes time. And then there's also this belief that no one can censor Ethereum for more than like a day or so. So those are kind of the factors where people socially agreed upon a week, but it is relatively arbitrary.
Vitalik tweeted it.
Pardon?
Vitalik tweeted 7.
But
Social consensus.
But is there a theoretical lower bound, as you said?
Monday.
You could probably actually go lower than 1 day. You would need to do some clock extension. So there's chess clocks per side, and if someone makes a move when you don't have much time left, you actually get an extension. So there's some bounds there where you could go lower. Maybe you could do 1 hour for the first move, and then like if someone hasn't responded, do an hour if no response, but if someone responds, extend it. There's options there. So the lower bound's actually probably a fair bit lower. Depends on it's kind of how long do you think someone could censor Ethereum for? Because you're relying on someone being able to step in the case of an attack.
Both censoring Ethereum, and you could even you could run a DOS attack, right? It's a very financially motivated attacker and I know that you're the only other person that runs this. And then I DOS you for an hour. And if I do that successfully, I cut your internet cable for an hour. And if I do that successfully, then I win. And I can cause like infinite or maximum damage.
No, the reason why, and there's an obvious reason why I'm asking, right? If you want to sell this to people in finance or financial institutions to use this in some form, then obviously a week sounds like a very, very long period, right? To wait for something to be final.
This is for withdrawals though. If you're in exchange, again, you only need to wait about half an hour to consider something final. In the back first?
Yeah, just so the fact that the challenge period is 1 week, does it affect in any way the frequency of the with whom you can post updates on mainnet? Meaning, what if you post an update today that's less than a week from the previous update, and then the previous update get challenged? Does it count as a kind of fork? Or
No. So we actually post very frequently. We post these state updates every hour, and each one is essentially independent of the other.
But if a past state update is challenged and turns out to be incorrect, then what's like transactions?
Yeah, so if a past one is challenged as incorrect and is shown to be incorrect, that does not invalidate any other state outputs.
Subsequent?
Yes, that is correct. Each state output is its own thing. They don't build upon each other.
So I understand that there's a sequence of transactions.
Yes.
So of course one update with the sequence of transaction turns out incorrect. Technically I have also the other sequence of transaction, but in the interpretation side, like essentially you are maybe you are removing some, you thought there was some transaction, but they are not there.
Mm-hmm.
And what's the meaning of the rest?
Does it matter?
I don't know. Like I transacted expecting that something was, so you are removing some data from, I understand that you can, but.
I didn't touch on this too much, but the fault-proof system for any rollup really is very disconnected from the rollup itself. It's like you're making a claim about what you think is correct on Ethereum, and that has no bearing on any other claim that someone else is making about the state of the rollup.
Maybe just in the interest of time, we can move on to the
Just
next
a quick question.
Very quick.
You can have an infinite number of rollups.
Roughly.
How does it scale, Ethereum?
Yes.
In performance and in storage?
Yes. Here we go. This is the last slide. Almost one more slide after this that you'll expect. Yeah, so why this works? Because we store transaction data instead of state. Again, that's cheaper. It's a whole talk on why the state is so expensive. Find me later. One honest actor. If you compare this to Ethereum, you need a large proof of stake, and you need 2/3 of those validators to be honest. Lastly, more on the social reason, rollups are where the experimentation is. And then our favorite slide.
So I'm just going to throw one comment in, right? So you say you need one honest actor. The problem is, if this honest actor can never earn any money because everybody else, all the sequences are always doing everything correctly, then there's no incentive for even one honest actor to be there. So how do you solve that problem?
Yes, there's a little debate here. They earn money if someone is attacking the system, so they earn money when they defend. They don't lose money by defending, but there is a capital lockup, which is tricky to deal with. And you have to run the watcher even if no one's attacking. So this is where you have people who are incentivized, like exchanges, like the roll-up operators, to go do this. So a little bit of you need some other reason to do in some cases.
Okay.
So.
Let's thank the speaker.